Now, section 6, we're finally going to get into conservation of energy. So all of these things that we've been talking about, we're going to put together and solve some problems. So conservation of momentum, we're doing before and after pictures. That perspective is important for conservation of energy as well. So the work energy equation that we've been talking about is here again. This is our form that we're going to be working with now. So kinetic final, potential final, energy, delta energy, thermal added together on one side equals kinetic energy initial plus potential initial plus work. So that's how we're going to start off our problems. So this form states that the system's final energy, including any change to the system's thermal, equals its initial energy plus any energy that we're going to add to the system as work. So we don't want to write energy thermal as thermal final minus thermal initial, because the initial and final values of thermal energy the initial and final values of thermal energy are typically unknown. Only the difference can be measured. So we just write it as delta thermal. If the system is isolated, then no work is done, remember, so work will be 0. And so that's how we're going to start off. Now, we have some different isolated systems to talk about. So an object in free fall, we have, notice the little like rope looking things around the system. So the item in free fall would be the force is on the ball or whatever it is going to be the weight of the object. So we have the force here is the earth on the ball, and then the earth is also being pulled upward, although it's kind of strange to think about action-reaction pairs, right? So we choose the ball and the earth as the system so that the forces between them are internal forces. So there's no external force to do work, so the system is isolated. So then no work is being done. An object sliding down a frictionless ramp. So notice the way that the system is drawn here. The external force the ramp exerts on the object is perpendicular to the motion. So the external force is perpendicular to the motion. The motion is down the ramp here, so the external force is perpendicular. And so therefore does no work. Remember, work is in the direction of motion, right? The object and the earth together form the isolated system. So no work is done here either. An object compressing a spring. So here we choose the object and the spring to be the system. The forces between them are internal forces, so no work is done. Okay? And then here we have the object sliding along a surface with friction. So the block and the surface interact with kinetic friction forces. So the object is sliding. You can see the little motion situation happening over here. These forces are internal to the system as well. So there are no external forces doing work, so therefore the system is isolated. So we're always trying to isolate the system so that no work is being done. And if you can do that, then you can simplify the work energy equation, and then the problem becomes easier. Okay? So if we think down here, a student is sliding down a rope using friction to keep her moving at a constant speed. How do you choose the system so that it's isolated? What would our system be?
The rope and the student and the earth.
Yes. So it's her and the rope. Obviously, they have to be part of it because she's holding onto the rope, right? But also the earth. So those three things would be our system. She's sliding down the rope. So we have kind of this situation here. Okay? The system is isolated, then no work is being done, and we would move on then with our work energy equation. So now we're going to use the law of conservation of energy. So here's your problem-solving approach. The work energy equation and the laws of conservation of energy relate the system's final energy to the initial energy, as we saw. So we can solve for initial and final heights, speeds, displacements from these energies. If you look back at what those energies were, so like kinetic energy, potential energy, each one of those had different parts to it, and they all relate to these ideas. Initial and final heights, speeds, displacements. We can get all of those. So to strategize, the first step we should do is look at the system. So figure out what the system is going to be, and then consider the situation before and after process. So decide on what is both the before and what is the after. And then just like for the momentum problems, draw your before and after visual overview. And then what do you know? What don't you know? Just like we've been doing basically all year long. And then again, here is your work energy equation. Start with that every time. And then maybe there's some things you can get rid of here. Maybe there is no work. Maybe there is no potential energy. Maybe there is no thermal energy lost. I don't know. Get rid of the things that are not needed. Then, depending on the problem, you're going to need to calculate initial and or final values and then solve for the unknown thing. And then whatever it is that you need, if you have friction, if you have drag, whatever, then check the sign of your energy. Remember this one, kinetic energy is always positive. It's as is the change in thermal energy. And check that your result has the correct units and it's reasonable and answers the question, as always. Okay, so pretty straightforward process. It's something we've been doing all year long. It's just that now we're using the work energy equation as our baseline. Okay, so now we can give something a try. Actually, I lied. We're going to talk about this first. So the spring into action problem, the locust can jump as far as 1 meter, an impressive distance. So it's just jumping 1 meter. The locust is actually pretty small. So to make the jump, the legs extend much more rapidly than the muscles can ordinarily contract. So instead of using its muscles to make the jump directly, uses them to more slowly stretch an internal spring near the knee joint. So this stores elastic potential energy in the spring. When the muscles relax, the spring is suddenly released and its energy is rapidly converted into kinetic energy of the insect. So this is just a biological example of the sort of thing that we've been talking about, to allow a massive amount of energy to be released and then in the form of like spring action so that this bug can jump 1 meter through the air. Tiny little thing, 1 meter through the air. It'd be nice if we could do that. So with that in mind, then the locust is an excellent jumper. Suppose a 2-gram locust leaps straight up rather than trying to leap across, it leaps straight up, leaving the ground at 3.1 meters per second, which is a speed that a desert locust can easily reach, 3.1 meters per second. So if we ignore the drag force, how high will the locust jump? And then B, if 20% of the initial kinetic energy is lost to drag, how high will the locust jump now? So we have the picture on the right-hand side. We have the before and the after. We want to find y final. So y initial then would be 0. Okay, what do we do? So the first thing we should do would be to draw a picture, and that was given to us, thankfully. So then after that, we're going to identify the things we know and we don't know, and that was given to us also. So we have the initial velocity is 3.1 meters per second. When it reaches its maximum height up here, its velocity will be 0 meters per second, and then it will start to fall again because it just jumped straight up and it's going to come straight back down. We're looking for y final. So that will be in part A with no drag, so no friction. So we're going to start with our work energy equation. So we have K final, kinetic final, plus potential final, and then plus delta energy thermal equals kinetic initial plus U initial plus work. So now our job right now would be to get rid of the things that are definitely 0. So what's definitely 0 here? Thermal. There is no drag, so we're not going to lose any energy to heat. Okay, what else is 0?
Work.
If we isolate the system, which we can do, because all we're doing is jumping up with this locust and coming back down. What is the system then?
The system would be the grasshopper and the earth.
the locust, the earth, and that's basically it, right? Then we can say that there is no work being done. Okay, is there anything else we can get rid of?
Potential initial, right? Because it doesn't really have any. I mean, after it jumps, it has potential for when it comes back down, but before it jumps, it doesn't have.
Okay, so for right now, you're not wrong, but for right now, I'm going to leave that on here just because I want to point something out. Okay, so for right now, let's call that good. So now let's turn these simple letters, the K's and the U's, into the formulas that they represent, right? So 1/2 mv squared for K final will be 1/2 m v final, right? Squared. Okay, now U final would be plus, what's potential energy? mgy. Yeah, sure. So we have m, g, and then y would be y final for this one, equals, now K initial would be
MVI squared.
1/2 mv initial squared, and then plus U initial would be
Mass times gravity times y initial.
mgy initial. Okay, so now let's go through this again and point out what I wanted to point out, which is why I didn't cross this off, right? So y initial is actually zero.
So that's gone.
So this whole term now goes away because of the y initial being 0. What else?
Velocity.
Velocity final is 0 when it gets up to its maximum height. So this term, kinetic final, is actually 0. And if you go back to when we were talking about kinetic energy, when the object is not moving, it doesn't have any kinetic energy, okay? So the locust, when it gets up to the top of its motion, it is not moving. Instantaneously, it's not moving. So therefore, it has no kinetic energy, okay? So back in the work energy equation up here, we could have said that and crossed it off. And we could have said here, well, when it's at the bottom, it has no potential energy. So we could have crossed that off at that moment also, okay? But I wanted to not do that just then. I wanted to show you why and why it has no energy at that point, okay? So even if we miss it here, we can catch it here. And even if we miss it here, we can catch it here. Okay, so our work energy equation now has just boiled down to this guy and this guy.
So we can solve for y final.
We're solving for y final. Very easy to do. Divide by mg. Now, if I divide both sides by m, what happens?
They're gone.
The masses actually divide out. Yeah, so those are gone. And so now all I have to do is divide by g. So I have y final equals, this would really be vi squared over 2 on the right-hand side right now. So what I have is vi squared over 2g. And I can plug all that stuff in because this is what we're looking for. How high will the locust jump? So the initial velocity was over here, 3.1 meters per second squared, meters per second, and this is squared. Divide by 2 times 9.8 meters per second squared. And what is it?
0.98.
No, it's 2 on the bottom.
Oh, I forgot the 2 on that.
So 3.1 is almost 9, a little over 9. We should be around a half. 4.49?
Yeah.
0.49 meters. So there you go. So it jumps half a meter straight up. Okay, now what if 20% of the initial kinetic energy is lost to drag? So how do we do that?
Find 20% of 4.49.
Is it that simple, just 20%?
Well, no, because we're looking for K initial.
Yeah, so we're going to have to go back to the work energy equation. Okay, so let me change colors so that we're not super confused. So back to the work energy equation. I'm going to go right back to the full on original, except for work, because we know that there's no work. So K final plus U final plus delta thermal, K initial, U initial. Okay. Now, we know from what we just learned that there is no initial potential. Gone. We also know there is no K final. Gone.
So how come there is thermal? I know it's probably bad.
Okay, so with drag now, that means we're losing energy to friction, which is going to create heat. So then there must be thermal. Okay? So that one's going to stick around. So now we have these three guys hanging out. Now the question is, where is this 20% going to go?
It's going to go with KI because
we're losing 20% of the initial kinetic energy to drag.
Oh, so thermal.
So it's going to go to the thermal.
Yeah.
Right? Okay. So we're going to have to say now that the thermal energy. So let's see how to write this. So we have the U final, which let's just keep that around. U final. Nope, sorry, wrong color. Don't want to be confused. Okay, so U final. Okay, now plus
20% of KI.
20% of KI, that's right. So 20% of the initial kinetic energy is lost to drag, which is the thermal energy. Okay, so plus 20. So 20% is 0.2 KI. And then that equals what is on the other side is KI. Okay, so now,
Make the equations, right?
Yeah.
See if anything can be.
I can move this 0.2 KI to the other side. So I'll have UF equals 0.8 KI. I just subtracted it from this left-hand side. I just subtracted 0.2 KI from both sides. So now I have 0.8 on the other side. Okay. So now I can convert. I have mg y final equals 0.8 times the ki, which is 1/2 m v initial squared. And now it's just a matter of solving for y final again. So the mass goes away again, and I'm going to divide both sides by g. I have the 0.8 times 1/2, but I don't really need to worry about solving for that, or I can, simplifying it, I mean. So let me pick the right color. Okay, so y final equals 0.8 times 1/2. Half of 0.8 is 0.4. We have vi squared divided by g. So now this will be 0.4. The initial velocity is the same.
Wouldn't it be over 2g still?
No, because I took 0.8 times 1/2 and I made it 0.4.
Oh, okay. Otherwise, it'd still be 0.8 over 2. Which, yeah.
Right. Yeah, I just simplified it. Okay, so then it's the same velocity divided by 9.8. So we did lose some height because of the friction due to drag. A little bit more realistic because of the air resistance. But there you go. That's how you do it. Okay. Now, the interesting thing is we did all this without the equations of kinematics, right? We just did it with energy, which is pretty cool. The Summit Plummet is an extreme water slide, one of the steepest and fastest in the world. So you go up 36 meters from the start until you hit a run out at the bottom. So So you're up 36 meters, and basically all you do is you just drop on the slide
So
36
almost
meters.
free
So it's
fall.
almost like free fall. Or it might even be free fall. I don't know. I don't know what this one actually is. But if you give yourself a good push at the start, so you begin your plunge moving at 2 meters per second, how fast are you moving when you get to the bottom is the question. So let's draw a picture. So the picture is going to look something like it sounds like as you read this, you're giving yourself a good push. So there must be some kind of little like ledge here, and then we got this wicked, and then we kind of taper off at the end. And then usually there's some kind of run out at the bottom where you can kind of safely come to a stop. If you're going fast enough, the game is always, if you're going fast enough, you try to run out all the way to the end of the track or whatever. But anyway, so I don't know. Is it total free fall? Probably not. And it probably kind of tapers out a little bit. Like I probably drew that way too steep, but who cares? Okay, so we have 36 meters here. All right, so here we are at the top. What are we doing? Are we sitting? Are we laying down? Does it say? Do we have to use a chair? What is it? Is it an inner tube?
I think it's just us.
Is it? We're just laying there?
Yeah.
Okay, so probably we're going feet first. There we are. It's going to be a great time.
Wow, that's definitely that's a person.
Yep. Okay, so we give ourselves a good push, and we're starting the plunge at 2 meters per second. So what does that tell us?
Velocity initial.
That's our initial velocity. So VI 2.0 meters per second. Also, we know that
Our Y initial.
Y initial is 36 meters.
So is Y final 0.
Y final is 0 meters. Okay, and what are we doing here?
We're trying to figure out how fast we are at the bottom.
Okay, so at the bottom, hopefully we're still on the track. And we're going to have V final down here. V initial up here. Y initial is up here. Y final is down here. Anything else we need?
Nope.
Okay, so in the work energy equation then, we would have what?
K final plus potential. No, yeah, plus potential final plus thermal.
Delta energy thermal equals.
K initial.
Okay.
Potential initial.
Plus work.
Yeah.
Okay. Now, can we close this system?
Yes.
Yeah, it's just us on the track sliding down. We're not putting any work into this, so work is gone.
And there's no thermal. Because it says you can ignore friction.
You could ignore friction right there, so we're going to get rid of thermal, which is good. Okay, what about any kinetics or potentials? Can we get rid of any of those?
You won't have any potential final.
Potential final is gone. We're at the bottom. How about kinetic? Can we get rid of any kinetic?
No, because you're starting 2.0 meters per second.
Our starting kinetic, our starting velocity is not 0, so we can keep the kinetic initial. And kinetic final, obviously, we're moving, so we can't get rid of any kinetic.
Have potential.
And we have potential at the beginning, yes. So we have to keep everything that's still there. All right, so now what do we do?
1/2 mass velocity initial squared is equal to.
1/2 mass velocity final squared
Oh, that's right. Yeah, my bad.
equals kinetic initial, so 1/2 mass velocity initial squared plus UI. So that would be
mass times gravity times Y initial.
Y initial, yes.
So we want to solve for VF, so we can divide by.
I see a couple question marks here. How fast are you moving when you get to the bottom? We're looking for V final there. How fast would you be moving if you skip the push? That's a part
whole
B.
different equation.
That's different. Yep.
Still
Okay.
be final.
Still
But-
V final,
But we would have.
but it's a part B
yeah,
V
it
final.
would- KI would be gone.
Yes. Okay. So this is part A that we're doing right now. Okay. So what can we do?
Multiply by 0.5, divide by mass.
I can divide mass out completely.
And then square root, multiply it by 2,
I would love to multiply by 2.
and then square root it up.
And then, yep. So we're going to have V final. I'm multiplying by 2.
So you're just going to be left with 1.
So that'll be VI squared plus 2GY initial. And then I'm square rooting the whole thing. Okay, we can totally solve for this. We have the square root of VI squared. So that's 2 meters per second. This is squared plus 2 times 9.8 meters per second squared. And Y initial, 36 meters.
Um,
26.63.
26.6?
Yeah.
So we'll call that 27 because it sounds faster. Well, how fast is that?
Wow.
50 something.
Oh, it's more than 50. 55 miles an hour. That's pretty fast.
And you're only traveling at 4 miles per hour before you start.
And you're in your bathing suit.
Could you imagine if you
That's a major wedge.
did a
Yeah.
full sprint and then into it?
Well, a full sprint, you're not even touching the slide, probably. You're just going to fall the whole way. And that's not going to be comfortable when you land.
No.
Okay, part B, we are nixing the push. So how does that change our work energy equation?
K initial disappears.
Okay, so we have K final still.
Equals.
We still don't have U final, right?
Nope.
Do we have energy thermal this time? Okay, so equals K initial.
It's out.
0.
There's no K initial. Do we have U initial?
Yep.
Yes.
Yes. Do we have work?
No.
No. Okay. No K initial because there's no velocity to start with. Okay, so now we can convert everything to 1/2 mv final squared equals U initial is
Yes. Yeah. MG.
g y initial. And once again, the masses can be divided out. Once again, I can multiply by 2 and then square root. So I have V final is 2GY initial, square root it. Okay, so this would be square root 2 times 9.8.
26.5.
26.5. Okay, so what was the other one?
It was 26.63.
So slower, but not much.
No.
Right? So 26.63 you said, and this one was 26.5. Wow, what happened there? Distracted.
It's
Okay.
26.56.
Okay, so this one is definitely faster than this one, but when we significant figure it,
They're the same.
it looks the same, which is kind of a bummer. But we know that that first push is going to put the person who pushed ahead of the person who didn't push initially. But the reality is they're going to wind up in about the same spot at the end because they're basically going the same speed.
So you just need to
at
push
the end.
faster.
Yeah, the push is what's going to make you win.
I would
If
have
you
thought
race
there would have been a
side by
greater
side.
difference, to be honest. I was expecting a bigger difference.
Yeah, I kind of was too.
It's a disappointment.
It's disappointing.
You were you've been teaching this class for how many years, and it still amazes you?
It's amazing. All right, the speed of a spring-launched ball. So the spring-loaded toy gun, I'm sure we all had one of those, is used to launch a 10-gram plastic ball. The spring, which has a spring constant of 10 newtons per meter, is compressed by 10 centimeters as the ball is pushed into the barrel. When the trigger is pulled, the spring is released and shoots the ball back out horizontally. What is the ball's speed as it leaves the barrel? Assume friction is negligible. So what's our first move?
Draw a picture.
Draw a picture. So we're going to draw a very innocent looking
Wow.
Yep. Inside is our wobbly spring, and we're loading the ball. Oh, wait, that's my after picture. Okay, very innocent looking before picture. Now the spring is loaded, and here's my ball. Okay, so this is before, and this is after. Okay, so here we have some information that was given to us. We got to kind of put that on here. It said the spring, which has a spring constant of 10 newtons per meter, is compressed by 10 centimeters. So here to here, we're compressed 0.1 meters. Okay, when it's released, we had 0 meters here. So this is X initial, and this is X final. Now we also know some stuff. We know K, the spring constant, is 10 newtons per meter. We know the mass of the ball was 10 grams. Now if I turn that into kilograms, I got to move the decimal 3 places. 0.01 kilograms. And then what is it I'm looking for here? The ball speed as it leaves the barrel. That would be V sub I.
That's the initial.
Initial velocity, yeah. No,
That'd be the final.
final velocity. We don't know that one. What's the initial velocity?
0.
Yeah, okay, good. So where should we start? Okay, the work energy equation. Are we going to have K final?
No, because it's 0.
We're not going to have a final kinetic energy?
That's
Okay, final. Yeah. Final.
Yes, K final. Are we going to have potential final?
No.
no, because we.
I'll tell you what, I'll write it down. We'll think about it. U final. Are we going to have thermal energy here?
No.
Why not?
Because it says friction is.
Friction is negligible, so no thermal.
Such a hard word.
Are we going to have kinetic initial?
Yes. No.
No, because there's.
I'm just writing it down. We'll think about it. What about potential initial?
Yes.
That's what's good.
What about work?
No. We can make this a system.
Okay,
Isolate it.
so no work is done.
Yeah.
Closed system. Potential initial?
Yeah.
Definitely. The spring is loaded. Okay. How about K initial?
No. Because it's not traveling.
It's not moving. No kinetic initial. Potential final?
Yes.
Yep.
Potential final?
Oh, potential.
We unloaded the spring.
Yeah, there's none.
There's none. Kinetic final? Yes. Okay, so we're down to kinetic final, which is going to be 1/2 mv final squared equals potential initial, which is for a spring, not mgy.
It's
1/2 K
squared.
x squared. Good job. Okay, so this time the mass doesn't divide out. I'm going to need it. What is it that I'm looking for? The V final. So I can multiply by 1/2 on both sides. And when I do that, the 1/2 goes away. I can divide both sides by m, and I can square root. So when I do that, I'm going to wind up with
kx squared. Square root kx squared over m.
you got it. And I know all that stuff.
Why is it kx? Is that just how it is?
This is the spring potential, that formula that we
Okay.
worked with.
Sounds good.
Okay, so we have K, which is 10 newtons per meter times X, and that was
0.01.
meter, and that's squared, divided by the mass of the ball, which was 0.01 kilograms.
Meters per
3.16,
second.
and it looks like we need two significant figures, so this will be 3.2 meters per second. There you go.